Hello and welcome to USACM UQ TTA webinar. Today we have Professor Youssef Marzouk. Dr. Youssef Marzouk is a professor in the Department of Aeronautics and Astronautics at MIT and co-director of the MIT Center for Computational Science and Engineering. He is also a core member of MIT's Statistics and Data Science Center and director of MIT's Aerospace Computational Design Laboratory. His research interests lie at the intersection of computation and statistical inference with physical modeling. He develops new methodologies for uncertainty quantification, Bayesian modeling and computation, data assimilation, experimental design, and machine learning in complex physical systems. His methodological work is motivated by a wide variety of engineering and environmental applications. He is an avid coffee drinker and occasional classical pianist as well. With that, let us welcome Professor Youssef Marzouk.
So thank you very much for the kind introduction, and thanks for having me as a speaker in this seminar. It's exciting to talk to this group and to see some old friends and many new people. So today I want to talk about some work that is in the broad problem of sampling. So I realize this is the UQ seminar, but the underlying problem of sampling is one that shows up in many situations in UQ. And essentially the theme of this talk is going to be some interesting methods that are, I think, under active development for solving various kinds of sampling problems in understanding properties of these methods, where they can be applied, and where they work well, where they don't, and things like that. In particular, I want to talk about sampling that uses transportation of measure, and in particular, sort of within that, I want to talk about dynamical representations of transport, and we'll get into what that all means. Before I dive in, I do want to acknowledge my sort of main collaborators in this effort. So on the top row are three of my PhD students: Amy Moray, PhD student in computational science and engineering; Panos Simpos is a second-year PhD student in operations research; and Robert Wren is a sort of final-year PhD student in math. And then two former postdocs, now independent faculty members on their own, Sven Long and Jakob Zek, also contributed to various aspects of what we're going to talk about here today. So they did all the good things. So, okay, the problem of sampling. So, sampling is really a ubiquitous problem in statistics and applied mathematics, certainly in uncertainty quantification, with a whole bunch of different applications. I will not be exhaustive, but I'll talk about maybe two relatively kind of representative versions of the sampling problem, and there's many that we won't be able to address. One flavor of the sampling problem is really the idea that I have the unnormalized density corresponding to some probability distribution, and I now want to draw samples from that distribution. So this is really the central computational problem in Bayesian statistics. So any single time that you write down the Bayesian model, very often you will write down the prior density, you'll write down a likelihood function, but that is only half the battle or a fraction of the battle. Your goal is to somehow draw samples from the posterior distribution. And to make this concrete, this is an example of some work that we did with collaborators in the Finnish Meteorological Institute on Earth remote sensing. And here the idea was basically to learn the concentrations of various trace gas species in the atmosphere. And here's the Earth's atmosphere, kind of like layers of an onion. And here's the Earth itself. And the imaging procedure was basically kind of a tomography based on an instrument aboard a satellite. And you'd absorb starlight. So you basically look at the spectra of the absorption spectra of starlight as the satellite moves around the Earth, and you essentially then get different cuts through the atmosphere, and from that you want to back out, okay, what is the actual profile, the concentration profiles in the vertical setting. So the details aren't terribly important. Essentially what I want to say is that X represents the unknown concentrations as a function of altitude, Y represents the absorption spectra or the data, and I can write down perhaps some prior density for X. My physical model tells me something about the probability density of the spectra given a particular state of the atmospheric concentrations. And then Bayes' rule tells me the posterior distribution of X given Y, or at least the density of that posterior up to normalizing constant. So the goal then is to sample so that I can tell you things about the uncertainty in the parameters. I can tell you about the probability that the concentration of the gas at some point exceeds some threshold, so on and so forth. And this inherits the kind of usual challenges of sampling. The posterior in many problems is high dimensional. Here, it really depends on how much you discretize the altitude coordinate. It's generally non-Gaussian, and if my model of the absorption process and the noise generation absorb the instrument is expensive, then each evaluation of the posterior density could itself be expensive. So these are kind of the typical challenges of sampling in the Bayesian setting. But the same kind of sampling problem of trying to sample from some probability distribution given this unnormalized density shows up in a lot of other areas, in computational chemistry and statistical physics. Very often I might know the energy of some configuration of molecules and I want to sample from the Boltzmann distribution. But there's variations of this. Maybe I care about rare events, maybe I care about the tails, maybe I care about the probability to transition from one well to another. So there are a lot of ways you can make this sampling problem more elaborate. But this is just one flavor of sampling problem. A different kind of sampling problem, one that's quite popular these days, is generative modeling. So here, rather than having an unnormalized density as our input ingredient, we have samples, and we want to generate more samples. So proverbially, people say, well, generative modeling is creating pictures of cats, given a distribution over pictures of over cats. But there's many, many more serious applications. And I would also mention that there's links between generative modeling and things like simulation-based inference, which is also a very interesting set of techniques, where essentially that setting, you're given samples from a joint distribution over parameters and data, and then you would like to generate samples from a conditional of that joint, because someone then tells you, well, the data are equal to this value, and I now want to slice the joint distribution at some particular value. So conditional generative modeling can be thought of as a way of realizing simulation-based inference. But the core idea here is that now I don't have a target density given to me, I just have samples from the distribution of interest. So the claim that I want to start the talk off with is that transportation of measure provides a unifying approach to many of these sampling problems. And what do I mean by that? So what do I mean by transportation of measure? The essential idea here is that I want to represent my target, my probability distribution of interest that I'm going to write as pi, and I'm going to use sort of common notation for measures and densities. I assume every measure I talk about is absolutely continuous, so I'll just use the same notation for densities. I want to represent my complicated distribution pi as the transformation of some simple reference distribution. So think of rho as something simple, like a standard Gaussian or a uniform distribution on RD. And now I want to find a function from RD to itself that pushes forward rho to pi. What does that mean? It means sort of intuitively that if I could draw samples from rho, and I apply t to each of those samples, the resulting samples, say t of z, will be distributed according to pi. More formally, it means if I want to measure the probability of some set under pi, I look at its pre-image under t, that's t inverse a, and I measure the pre-image under rho. So this would be a very useful thing to have. If I can construct such a map, in some sense, I've solved the sampling problem because I've chosen rho to be something that I know how to sample from, IID, independent and identically distributed, so I can just evaluate t on samples, so I have embarrassingly parallel, independent, unweighted samples from the target, which is really the best you could ever hope for from any kind of Monte Carlo method. In practice, of course, t is going to be approximate, so we're going to talk about how that arises. And I'd also say that as long as you guarantee that t is invertible and differentiable, then you can essentially write expressions for the density of the push forward and also the density of the pullback. So just to set notation, in red, the superscript sharp here means pullback. So essentially this means applying t inverse to pi. So pushing forward pi under t inverse. That's what I mean by the pullback notation. And the subscript sharp means push forward. It means take t and push it, take rho and push it forward via t. Okay. So by the way, if you have questions, feel free to interrupt, but also we hopefully will have time for questions at the end. So however we want to do it is fine with me. So, okay. So this is sort of a nice notion. If I had a transport, I would be happy as someone who wants to solve the sampling problem. The first question you might ask was, well, does such a map exist? And the answer to that is relatively easy. Essentially for absolutely continuous rho and pi, there always exists a map. The problem, in fact, is that there's infinitely many maps for any given pair, rho pi. And here you have many choices. And this is really where the game begins. What t would you like to realize? And what is, in some sense, easy to construct, easy to approximate, easy to build from a finite set of samples? These are all now the design questions that start to enter these methods. One natural map to think of that probably you're familiar with is the notion of optimal transport. So of all the different ways to push forward rho to pi, I want to do so in some way that minimizes some sort of integrated cost for some ground cost that I pick, maybe distance or distance squared. But I could also consider other ways of pushing forward rho to pi. For instance, triangular maps is something we've thought about a lot in the past, where you sort of push forward rho to pi coordinate by coordinate, but where you pick a particular ordering of the coordinates. And you do the first coordinate first, you match the marginals, and then you match the conditional marginals of the second coordinate and the third, and so on and so forth. These are kind of canonical maps, and they're quite useful in the sense that people know a lot about them, but our attention is not going to be limited to these canonical transports. So in that larger sense, what we've done is really just move the problem. I've taken the problem of sampling from some distribution on RD, whether it's the result, the solution of some Bayesian inverse problem, whether it's a problem of generative modeling. I've taken this problem and just transformed it to find me a map from RD to itself. Within this setting, now I need to ensure invertibility, and I need to ensure differentiability and say easy evaluation of Jacobian determinants, because these are going to be things that show up a lot. I'm going to have a lot of Jacobian determinants that show up in various points of this problem. And there's a multitude of choices. What I want to do is kind of give a very broad overview of different choices that have appeared in the literature and categorize them in two different ways. I want to talk about static approaches to realizing transport and contrast them with dynamic approaches to realizing transport. So what do I mean by these things? Static, essentially, I mean, you represent the desired displacement field directly. So this is saying if I want to look at, this point here that I'm sort of highlighting with my cursor, I want to essentially map where this point goes to here. So I essentially want to parameterize T directly. This point goes over here, this other point goes over here, actually capturing the displacements. Many ways to do this. So normalizing flows are one common way of doing this, which are essentially compositions of relatively simple maps interleaved with permutations. You could autoregressive flows, compose triangular maps. There's a lot of other things you could do. Typically, some aspect of these maps is parameterized with deep neural networks. You could also say, I want to find certain canonical maps. Triangular maps, monotone triangular maps, essentially give you approximations of the canonical Noeth-Rosenblatt rearrangement. And for any given sort of ordering of the variables in my target density, there exists a unique triangular map that does the job that will, in one shot, push forward the reference to the target. And you can represent these in various ways by monotonizing polynomials or other kind of, nice linear bases. I could also say I want optimal transport maps. And one way of approximating optimal transport maps would be to say, let me approximate convex functions, because I know that, for instance, like, L2 optimal maps are gradients of convex functions. So I could use input convex neural networks to approximate these potentials and take their gradients to find optimal transform maps. Many things you could do. And you could do the same thing for conditional sampling to get conditional optimal transform maps. So these are all various options. A different class of approaches says, let me represent the transport not all at once, but let me do it incrementally by thinking about the evolution of the points that I'm trying to transform over some fictitious time. Now here, we could think about things like neural ODEs, and we'll talk about those in quite a bit of detail later on. You can interpret these as continuous time normalizing flows, where I just take little steps as I go. Flow matching methods are another sort of, and stochastic interpolants are closely related. These are another ways of essentially trying to find transformations over some unit time, where I find some velocity, some incremental displacement that takes me from one distribution at time 0 to another at time 1. In a different vein, people have constructed a lot of interacting particle systems that sample, maybe in some cases approximately from a target distribution. So ensemble Cannon samplers are one, interacting Langevin diffusions are another, or discrete time dynamical systems. There's sort of work that says, let me discretize on Newton iterations in some way to realize a transport from one distribution to another. All of these dynamic approaches essentially say the supposition is that somehow introducing kind of a time variable or doing things incrementally is beneficial. And this is something that we wanted to look at and start to understand. So this is really going to be the core focus of this talk, is developments and challenges in dynamical representations of transport, realizing that if I can represent these transports in various ways, I could solve a lot of practical sampling problems, ranging from inference to generative modeling and beyond. So if I want to start kind of looking at these dynamical transports more carefully, the recurring structure, the thing that really I think unifies is almost all of them, maybe not quite all, but many of the methods that have been proposed, is that they represent the transport as the flow map of an ODE system. So here, just a set notation, capital X is the state of my ODE. F is the right-hand side. I'm going to call it a velocity field. And this is a velocity field that depends on the state and time. So this is in general non-autonomous. Little x is the initial condition. So capital X is really a trajectory of the ODE beginning at time little x, or beginning at point little x and evolving with time t. So how do I write these trajectories? Where I can essentially integrate the right-hand side. And from this, I can derive the flow map. So I can essentially say, okay, let me fix some time little t. And the flow map is essentially what takes the initial conditions and maps them to the state at time little t. And without much loss of generality, I could just fix little t to be 1 and consider the time 1 flow map. So this is essentially the mapping of the initial condition to the time 1 state of the ODE. And this mapping is parameterized by the velocity field f. That's why I'm going to have the superscript f right here. Okay. So this is a way of parameterizing transports. Why might you want to do this? Well, one thing is that, is for really, relatively kind of mild and natural assumptions on the velocity field, the flow map TF is guaranteed to be invertible. One way of thinking about this intuitively is that sort of the paths of the ODE, the trajectories of the ODE do not cross, they don't touch. So I can integrate forward, I can integrate backwards. So this is in contrast with things like normalizing flows, where you need to do some work to ensure that things are invertible, or even with triangular maps, you need to do some work to ensure that things are monotone. Here you get invertibility for free. Also, if you care about the push forward or the pullback density, there's relatively tractable formulas for these things that are called like instantaneous change of variables. So what this does is sort of opens up really generic choices of function class for f. If I happen to pick f to be a neural network, then this is called a neural ODE. But I could also pick f to be a polynomial, I could pick f to be like kernels, I could do a lot of different things. And the other thing that I would note that, if you're kind of, a practical ML person, these are the models that at least nowadays really achieve leading performance in many applications. So, okay, there is kind of an interesting then thing to analyze, but I have to say, at this point, it's not at all obvious that these representations of transport should be particularly, good or beneficial, other than the fact that, you have this convenient way of parameterizing things just by picking a velocity field f. So now some questions that sort of motivated things that we've been thinking about in this regard. One is kind of on the theoretical side, you like to say, okay, well, how well can these things approximate distributions? And if I train them with a finite set of samples, how good of a job can I do approximating distributions? And does this depend on things like smoothness of the densities? And how does this compare to, other really classical distribution learning methods? How does this compare to things like, wavelets or, kernel density estimation or something that seems very primitive by comparison? So that's one set of questions we'll try to look at. Another one is, what do we do with the freedom that is afforded by time? How do we design the dynamics and the evolution over time in a way that makes it somehow more advantageous than just learning a displacement? And for this, I want to make kind of a point, which is that we already decided that for a pair of source and target measures, rho and pi, there's infinitely many transports that we're going to push forward rho, say here at time equals 0, to pi at time equals 1. Many different displacement fields are going to get me this, express this bimodal thing as the push forward of the Gaussian. But on top of that, there's many different velocity fields that realize any given displacement. So there's kind of an extra layer now of infinity around the whole thing, which is that, I could take this point to this point and take an excursion over the time axis here. This horizontal stretch here is time equals 0 to time equals 1. I could take some funny excursion, or I could try to go here in a relatively straight line way. This is a choice. These are different f's that are going to give me exactly the same TF. So what do I do with this extra freedom? Is it helpful, or does it lead to new challenges? And, the answer is, in fact, a bit of both, as we're going to see. Okay. So these are things now that kind of, we'd like to understand better about dynamical representations of transport. So I'm going to have a couple of vignettes in the talk that show some different constructions, because there's really, a zoo of different constructions one could develop here, and different constructions useful for different settings. The first thing I want to talk about is neural ODEs in the setting of essentially generative modeling. So I'm given samples from the target distribution, and I want to learn that distribution by essentially learning the flow map of a neural ODE, which means I want to learn the velocity field of that ODE. So that's the setting we're going to see here. So for the purpose of analysis, we're going to pick some sort of simple settings, and I'll try to keep this relatively kind of intuitive to give you a sense of, whoa, what are we really trying to do in the analysis? So we're going to work on bounded domains to avoid a lot of technicalities. I'm going to assume my reference density is just uniform on the unit hypercube. We're in d dimensions. I have a target density that's bounded above and below. And now the velocity field is really going to be defined on a space-time domain. So the unit hypercube cross the 0-1 interval. The 0-1 interval is the time domain. It's the time interval in which we live. So, okay. So first, like, what kind of velocity fields can we think about? So this is essentially a minimal requirement on the velocity field for the flow map of the resulting ODE to be a diffeomorphism. So the velocity field itself has to be C1, and there's essentially kind of a no-flow boundary condition at the boundary of the domain. So this is the unit normal to the boundary, and this has to, so f has to not point into the boundary of the boundary. So under these kind of minimal requirements, then essentially the flow map associated with ODE is a diffeomorphism for any time. And why do we care about that? Well, now we can actually write the pullback density explicitly. So this is sort of an explicit formula for what I get when I take this flow map, XF, and I pull back my reference distribution, which happens to be uniform, but this formula is in general. Essentially, all I do is take that reference density, compose it with the map, and multiply by the Jacobian determinant of that map. So I just need these things to be well defined, and there we go. I need this thing to be invertible and to have a differentiable inverse. So now essentially we can use this as the object that is going to approximate my target distribution. So my approximation of the target is essentially what do I get when I take my reference and pull it back by this map. Okay. You might think, why did I do the push forward? Well, these things are invertible, and this is essentially just easier to write. But these are pretty equivalent things. So now the problem setup, as I said, is really learning from samples. We're kind of in that generative modeling flavor of sampling where I have capital N IID samples for my target, and I have some class of velocity fields that's in my sort of minimal class of velocity that satisfies my minimal conditions. In addition, has some extra bounds, and these are essentially associated with the lower bound on the target density. I have this target, this time one flow map, and now I want to solve a maximum likelihood problem. This is really the training problem that people do when they build neural ODEs. They're really doing maximum likelihood. Why do I think about this as maximum likelihood? Essentially, this expression here that I'm outlining with my cursor is PF pullback rho. This is my model for pi. And so I'm going to evaluate my samples, xi, drawn from pi, according to the log density of this model. That is the likelihood associated with the samples. And I'm going to try to find the f that makes these samples look as likely as possible. So I'm going to maximize this log likelihood objective over a class of candidate velocity fields f. So this is really kind of the chain of things. There's velocity fields parameterize maps. Maps give me approximations of the distribution of interest, and in particular its density. And now I evaluate the density on the samples, and that's the log likelihood. That's evaluate the log density on the samples, and that's log likelihood. So now, okay, we want to sort of understand how well can I do with a finite set of samples. So we really want to understand kind of like non-asymptotic finite sample statistical convergence guarantees for these kinds of models. So this is a little bit technical, but I'm just going to maybe give you some intuition. Essentially, what we want to do is bound something like the quantity on the left here. So I'll just kind of interpret this quantity here in my cursor is. Essentially, what I'm saying is, okay, I have a maximum likelihood estimator that I'm calling f hat ODE of the velocity, and T pullback rho is my model for the distribution, and I'm going to look at the Hellinger distance between that learned distribution and the target. Now, I learned this velocity field from a finite set of samples n. So in that sense, this error is random. Its randomness depends on the finite set of samples n, and let's just look at the expected error. And what I want to do is now bound this expected error by two terms, and essentially the two terms on the right correspond to kind of a bias-like term, essentially an approximation error associated with my velocity field class, and a variance term. This is essentially a fluctuation, again associated with the velocity field class. And what do these two terms depend on? This, in some sense, holds for any f star in my class, but I could think of wanting to pick f star as like the best approximation in my class. So I have a class of velocity fields that may or may not be able to exactly capture the distribution that I care about, but let me make this term as small as possible by saying, okay, let me pick the best approximation. In fact, this holds true for any, but I will probably tighten this down the most by picking f star to be the best approximation. Okay. But there's a price to pay, which is that maybe I need to make my class of velocity fields pretty big, pretty expressive, in order to capture some complicated distribution. And then this approximation error will be small, but this price is statistical fluctuation, because I'm trying to pick velocity fields in that class using only a finite set of n samples. And so the more complex the class is, the bigger the statistical fluctuation is going to be. So this is an intuition behind kind of actually a classical theory for non-parametric M estimation, where the statistical fluctuation depends on a notion of metric entropy of the class. And so this is essentially kind of looking at the covering number. So here's my velocity field class. And I'm trying to see how much can I cover this class with balls in C1 norm, and why C1 norm will become apparent in a second, balls of increasing size, and then I essentially compute this metric entropy integral, and that gives me the size of this term here. So this is a bit of an abstract theorem, but the point to really kind of think about this is really a trade-off between approximation error in the class and statistical complexity of the class. So it's a trade-off between bias and variance. Now, in our theory, basically what we did is we linked this complexity to C1 metric entropy and looked at, what are these ODE type MLE estimators really doing? They really depend on kind of a chain of stability results. They basically say, like, okay, if I have two velocity fields that are close in some sense, that should mean that the resulting transport maps are close in some sense. And that should mean the resulting distribution approximations, the densities, are close in some sense. So based on that kind of chain of stability results, you can then, put together a result like this. But at this level, it's relatively abstract. So this is kind of the meta theorem that now we want to apply to specific classes of velocity fields that we might have to learn over. For instance, polynomials or kernels, or in the case that I'm going to show you now, neural networks. So the point is that we want to bound and balance terms for some class of distributions, and then for some approximation classes, where the approximation class, crucially, can get bigger as your sample size goes up. So, and that's very natural. So as I get more samples, I have to be able to learn over more complicated classes. So, okay. So now I want to kind of, step under the hood one more time, which is to say, okay, if I want to approximate, for instance, a smooth density, this is a class of distributions I might care about, distributions that have densities that are CK smooth. What can I say about the velocity fields that are associated with those densities? So it turns out that there exists a velocity field that is also CK smooth if the densities are CK smooth. The CK smooth then also satisfies our minimal conditions for everything to be diffeomorphism. Now, this is actually sort of something that you do constructively, and you can do this many different ways. Here we happen to use the Noeth-Rosenblatt map, and to consider essentially the straight line interpolation of that map. And I want to point this thing out because this is going to show up later when we think about what's the best way to use time freedom. Here I'm going to use time freedom in a very, very naive way, which is to say, I have a transport that pushes forward pi to rho, and I'm just going to interpolate it with the identity as a function of time. So t equals 0, I'm going to get the identity, and at t equals 1, I'm going to get this t. So from this transport and this interpolation of transport, you can actually say, what is the corresponding velocity field that realizes the straight line interpolation? And you can write this thing down analytically, but instead of showing you the equations, I want to show you a picture. So this is really kind of the viewpoint of how do you go from displacement to velocity, and also how do you go from a Lagrangian picture to an Eulerian picture? I'll explain what that means in a second. So the straight line velocity essentially does this. I sit at some point x. I know that this should map to t of x. And I want to essentially find, the straight line interpolation of those things. That means that this point, this blue point, is going to proceed to the right with a constant velocity from t0 to t equals 1. This particle, if you will have 0 acceleration as it walks along this line. Now, a neighboring particle at the point x prime might have a different velocity, and the velocity is entirely determined by how far it has to go at time 1, and it's just going to take that velocity and spread it equally over time. So it's going to basically spread the displacement equally over time. So if I want to know now, that's the Lagrangian picture. If I want to know the Eulerian picture, if I want to sit at some point in this like space-time domain and say, what is the velocity that I experience at this point? Well, what I need to do is to say, okay, well, what is my initial condition? What's the initial condition that led me to this point? Follow the line back. How far does this point need to go? That's the displacement, and divide by unit time, divide by 1. So essentially, I need to invert and then evaluate t on the inverse. And that is precisely what this equation is here. So this is essentially the inverse, and then evaluate t in the inverse. Okay. So the point of this is now I can write down actually the velocity analytically, and now I can go through a bunch of things that says, well, I know the transport maps inherit some regularity from the densities, and then the velocity, because I can write explicitly, inherits some regularity from the transport, and so on and so forth. So the upshot is now I know that there exists a velocity field that will exactly represent this distribution that is CK. Now, okay, suppose I want to apply this to neural ODEs. I'll say, okay, well, how well can my neural ODE, how well can my neural network approximate these velocity fields? Now I know something about the smoothness of these velocity fields. And how complex is the neural network class from the standpoint of its metric entropy? So now I essentially can instantiate the approximation term over here and the statistical fluctuation term. I can now give these things very concrete identities, and I can now say things like, okay, if I construct a neural network for velocity fields, where the size of the neural network, depth, width, sparsity, so on and so forth, scales in a certain way with the sample size, that I can put things together in balanced terms and get the optimal rate. And so this is the result of that. You can essentially say that if I'm going to learn neural network representations of my ODE velocity field and use them to represent distributions, then if I scale things in a certain way, then the best that I can do, according to this construction, is essentially this rate in the sample size, where K is the smoothness of the desired densities, and D is the dimension. So this is kind of, to our knowledge, so this is kind of the result here. And to our knowledge, this is the first statistical convergence result for neural ODEs, for these ODE representations of transport. So, it's quite technical, but we're going through this whole exercise and we say, now we step back. Okay, are we happy or are we not happy? This is the rate that we got, ignoring the log n factors, which are kind of typical. And we can compare this to what is known to be the optimal minimax rates for density estimation. So these are things that kind of transcend method. And we see we're actually a little bit suboptimal. We're suboptimal in two senses. We're a little bit not taking full advantage of smoothness. We have a k minus 1 rather than k. And we're not taking full advantage of dimension. We have a d plus 1 rather than d. So, okay. They might say, okay, well, this is technical, and if I'm large d, then, so I should say, all of this is bad in large d. All of this is sort of exponential dependence in d. So one thing that I'm not talking about, which is a different sort of, thread, which is, okay, how do these things take advantage of like low dimensional structure and so on and so forth? We're not talking about that here. We're just talking about the kind of very basic vanilla estimation. So, but the d plus 1 rather than d is actually somewhat more fundamental. And this has to do with the time freedom. This comes back to like, are we using time in an optimal way? Well, where did this d plus 1 come from? It came from the fact that we're approximating functions of d spatial dimensions in one time dimension. But we did so in a very generic way. We looked for neural networks that were functions of space and time, which is often what people use in practice. So this kind of suggests, the analysis suggests there's sort of too much freedom here. And you can reconcile this with some practical trends in neural ODEs, which is to say, well, maybe we should start to regularize the training objectives. Maybe we should, somehow penalize too much, wiggling around as you get from time 0 to time 1. Or maybe we should do something even more strict, which is to impose certain intermediate target marginals as you go. So don't just say where you need to be at time 0 and where you need to be at time 1. Actually impose all the waypoints along the way. So this is a much, much stricter version of the learning problem than what I just described. So these are actually good ideas, and they have some sort of basis in theory. So in the interest of time, I'll just kind of mention very briefly this kind of ongoing project, which is to say, okay, can we tame the time complexity by picking an ansatz for velocity fields that is more restricted in some way? And can a more refined velocity field ansatz yield sort of optimal rates? I'll just kind of give you the intuition, which is that, as you probably now guess, time and space should not be treated equally. We should somehow limit how complicated things should be in T. And the inspiration is actually to represent invertible functions as compositions of near identity functions, and this in general can be done, but where we are being incremental, but the point is that somehow the number of steps in this composition should not increase with sample size, but somehow a finite set of compositions is enough for any given distribution. So this is where we were letting things get too complicated with sample size earlier. So now the number of steps in this composition only depends on t. And these are invertible as long as the switch constant is strictly bounded less than 1. So here's kind of a picture of the new ansatz and what this looks like. And what is interesting about this, I'll just kind of give you a kind of glimpse, is that these kinds of functions can really be represented, the velocity fields associated with these things can really be represented using fixed point iteration. So this whole thing actually really starts to look like a ResNet architecture. It really looks like an invertible ResNet architecture. And this essentially accommodates this image. So the fact that this is invertible essentially relies on h being small, and this is how you would construct invertible ResNets. And so this kind of ansatz is somewhat more complicated. And this is, I think we're maybe a few weeks away from finishing this, is that if you do things like this, you actually can achieve the optimal min-max rate. So there's a lot of details here, but the point is that somehow constraining that time freedom actually motivates some very practical neural network architectures that actually are optimal distribution learners in this setting. Okay, so maybe the takeaway from this is that you should use time, and being incremental is helpful because it lets you do things like keep these h functions very small, but being arbitrarily complex in time is more than you need. So, okay, this is, one perspective on a lot of methods that try to learn velocity fields and pick the class of velocity fields and try to make them into efficient distribution learners. But the other kind of vein that I described of how to regularize this kind of dynamical problem is to say, let us actually now not just impose an ansatz on the velocity field, but impose an ansatz on the distributions that you visit at every single step in time. So this is a stronger straitjacket, if you will. So now we're being even more prescriptive. But this actually leads to a different vein of dynamical approaches that could avoid neural network training and optimization altogether. And the motivation for the approaches that I'm going to describe here are really problems where they're of the first flavor of sampling that I described, where now I have an unnormalized target density. So we're shifting gears away from the generative modeling world to say, okay, someone handed me an unnormalized target density. In particular, actually, I'm using pi1 here to represent the target. Suppose all I can do is evaluate the ratio of the target to the reference up to a normalizing constant. And I can generate samples from the reference, but maybe I don't even know the density of the reference. So all I really know is pi1 over pi naught up to a normalizing constant, but I don't know pi1, and I don't know pi naught. All I have are a bunch of samples of pi naught. Now, why would I care about this setting? The motivation for this setting is actually problems like data assimilation. So this is really, I should also say, I also want to consider this setting where I can't evaluate gradients of this ratio, this likelihood ratio, pi1 over pi naught. This is really the setting for things like ensemble filtering and data assimilation, which is something that I've been interested in for quite some time. In this set of problems, they're really sequential inference problems, where at any given time, I have a prior distribution that is known only through samples. I have an ensemble of states of the weather, if you will. And I can evaluate a likelihood function, and using that likelihood function, I somehow want to update that ensemble from a forecast or prior ensemble to an analysis or posterior ensemble. So I have particles, and I really want to operate at the level of particles, but I can evaluate a log likelihood in closed form. So this is, what do people do in this context? Well, if you have a huge computational budget and you're small dimensions, maybe you should do some sequential Monte Carlo. But the really kind of workhorse algorithms are things like ensemble common type methods for approximate sampling. So I'll describe these in kind of one picture if you're not familiar. This is really a setting where, okay, I have some dynamical system that's evolving in time. These dots here represent samples of the state of the system at time t-1, conditioned on observations I've obtained up until that time t-1. I apply my dynamical model. This takes those samples and sort of advances them forward 1 unit in time. So now I have samples of the state at time t, conditioned on data only up until time t-1. So this is my prior ensemble. whose density I don't in general know. I just have samples. And then now I want to condition on some new data. I know the log likelihood up to a constant, and I want to somehow transform these gray samples to this configuration that should be their posterior. So I'm going from conditioning on samples up until time t minus 1 to data up until time t. Yeah. So in the dotted box is Bayesian inference. The data assimilation person calls this the analysis step, but this is Bayesian inference. The ensemble Kalman filter essentially moves the samples from the left here to the right using an affine transformation. There's no weights, there's no resampling, which is great. That's part of why it's scalable, but the transformation is very simple. And it's just estimated from essentially second moments of the ensemble and cross covariances of the state with the observations. So this is a very useful algorithm, but it is not consistent outside, in general, outside of like the linear Gaussian case. So if you have a linear Gaussian problem, this is a Monte Carlo approximation of the Kalman recursion, and it would converge as the number of samples goes to infinity. But outside of that linear Gaussian setting, in general, it does not converge to the true posterior. But peeking at this thing, you should say, well, this is transport. I somehow want to take these samples from some distribution, call this now pi0, and transform them to samples from pi1. So I now just want to find some transport. So can we sort of improve the analysis inference stuff via transport? So what I want to describe here now, going back to what I was saying earlier, is now I want to get from time 0 to time 1, but I want to be really prescriptive about how this is done. So now I'm going to kind of go, not just maximum likelihood training, I'm going to say, you know, thou shalt follow this path from pi0 to pi1. And this is one particular choice. Now, why this choice and what's good and bad about this choice, we'll get to in a second. But let's just say I want to follow this path. I want to go from pi0. All I know is pi1 over pi0. So essentially, I can evaluate this thing up to normalized constant, and this is just tempering with t. T goes from 0 to 1. And here's a picture of that path. What I want to do in particular is now find an ODE. So we're still in the framework that I described, where there's an ODE. I want to find its velocity field, and I guess here I'm calling v. Except now this velocity field is actually going to depend on the distribution at time t. So it's kind of a mean field ODE. Rho t is the current distribution of the particles, if you will, at time t. And I want to build an ODE that essentially, who's such that the law of the state, rho t, approximates my desired path, I t. So how could I do this? First I'll say, how can I interpret this path? There's many ways you can interpret this path. You can think about this as a gradient flow in the Fisher-Rao geometry of this log likelihood from time 0 to time 1. So if I start at time 0, if I start at pi 0 and I go integrate this gradient flow to time 1, I will get to pi 1. If I integrate this to time equals infinity, I'm actually going to get to a maximum likelihood point. I'm going to get to a maximizer of log pi 1 over pi 0. Another way I could think about this is as a Fisher-Rao gradient flow of this forward KL divergence, but rescaling it to unit time. Another way I could think about it is as sort of a barycenter of pi 0 and pi 1, where the weighing depends on where I am at this intermediate time. So it's kind of a weighted mean of pi 0 and pi 1 in this KL sense. But anyway, how do I construct a velocity field to do this? Well, essentially, this kind of comes back to sort of fluid mechanical or continuum mechanics intuition. I need to satisfy a continuity equation. I've prescribed a sequence of velocity field, or a sequence of densities pi t, and I want to find a velocity field that does the job. So essentially, I need to look at the derivative of the density, and this is something I can compute. And now I want to find a VT that solves this equation. There are, in fact, infinitely many VTs that solve this equation. I could impose a further constraint that I want this to be the gradient of some potential. This kind of gives you minimum energy in some sense. And if I do that, then I have a Poisson equation. So now I'm looking for a potential phi that satisfies this weighted Poisson equation at every single time t, where the right-hand side comes from the path of measures that I want to follow. And now this, okay, so now this is a d-dimensional Poisson equation. How could I solve this? Basically, in short, I'll say that we kernelize it, and we try to find the velocity field in some RKHS. So essentially, I kind of lift this whole thing up, I solve it in a weak form, and that takes care of all this integration against pi t, and we essentially write kind of kernelized versions of the solution operator for this Poisson equation, right? And so this m pi inverse is like the solution operator. And so skipping over some of those details, essentially now what I can do is I can write this in mean field form, using a bunch of, using some chosen kernel K, and I can actually discretize this now with a finite set of particles J, and this is now the thing you can actually integrate. So this is a set of J particles. The particles form the centers of kernels. The kernels are used to approximate the potential of the solution of the Poisson equation, and then the gradient of the potential gives me the velocity field, and then those particles then step forward according to that velocity field. So in some sense, there's basically, in discrete time, you'd imagine there's time integration, solve the Poisson equation, time integration, solve the Poisson equation, so on and so forth. So the particles are talking to each other. It's an interacting particle system, not unlike an ensemble common sampler, but where now we solve this Poisson equation generically. I should say that if you pick the kernel to be something very simple, like a quadratic, if you picked a polynomial kernel of degree 2, you actually recover an ensemble common type approach. But if you pick the kernel to be something bigger or something universal that's not finite rank, then you can converge to the true solution. So one way to think about what's happening here is that we're essentially kind of taking this Fisher-Rao gradient flow, which essentially corresponds to reweighing things. Pi1 over pi naught is like a weight. It's like saying I have a bunch of particles and we're trying to reweigh them. And we're trying to approximate the result of reweighing things by moving things, because I don't want to introduce weights, but the weights tell me locally how the distribution ought to change, but I'm going to mimic that by instead moving the particles incrementally and then computing the weights again. So I'll just kind of show you this movie to kind of show how things go. So here is just a kind of illustrative example. I'm going from a Gaussian in 2D to this kind of ring thing, and these are some particles using a version of the algorithm, and they sort of follow each other and interact and do something like this. Here's different kind of illustrative examples, and you can see you can sort of go from unimodal to multimodal things and certainly capture non-Gaussianity and things like that. Now, I can compare this to other derivative-free samplers. So other samplers that basically rely on being able to calculate a log likelihood ratio up to normalized constant, not being able to compute gradients of anything. So this takes things like longevin sampling off the table, and essentially using finite sets of particles. And you can see this is essentially the kernelized time discrepancy for a fixed number of particles as I discretize that time interval more finely. And these are KFR flows, the algorithm I just described. KFR flow I is sort of a variant of it, and these are ensemble common inversion, ensemble common sampling, consensus-based sampling, different algorithms like that. And it does reasonably well. Now, okay, I don't want to give you the impression that this is like a sampling algorithm that you should go off and use in a 500-dimensional problem and it's going to do great. This is not at all at that level. Like, we're doing this in relatively low-dimensional things. There's many issues when it comes to scaling, one of which is certainly how do you scale up kernelized solutions to the Poisson equation. And we can talk a lot about that. How do you impose low-dimensional structure? How do you localize? We're playing with things like random Fourier features, a lot of things to kind of scale it up. But I want to focus on a sort of complementary question, which is the choice of path. We picked this geometric mixture path, but the same machinery that I described can actually apply to any path where essentially the time derivative of this log density is tractable. So this is actually really kind of a meta algorithm with which I can put in a lot of different paths. And other things have been proposed, like even in yield importance sampling, people thought about sort of arithmetic mixtures, geometric mixtures, and a lot of things in between. It's like these Q paths. So the broader question that I want to come to is, well, what's a good path and what's a bad path? And what are good time schedules along a given path? And what do we even mean by good? So I would claim that what we really need to do is now think about like what a given path induces a velocity field, and is that velocity field easy or hard to approximate? And it's easy or hard to learn from finite numbers of samples. And also I need to think about time integration error and things like that. So how do I start to balance these different things? And what do we mean by good? So let me give you an example of, for instance, when does the geometric path, the Fisher-Rao path that I just described, behave very poorly? So this is an example that's called teleportation behavior in literature. So I start off with a standard Gaussian, a Gaussian was sort of a scaled standard Gaussian, and then the target is this Gaussian mixture. So I'm going to start off here. but the target essentially has two components to its mixture, one that's close to the starting point and one that's further away, though none of them really overlaps the starting point that much. So here's what the algorithm does. It's doing a great job pulling the samples towards the first node. The red dots are samples produced by the algorithm. The contours are the exact mixture density. So the exact thing that I want to follow. So there's no numerical approximation in the contours. The contours are what I really wish I could follow. They're the pi t. But now we're humming along, and we're getting close to time equals 1. And then look for what happens. Getting close to time equals 1. Something shows up over here. The second mode, essentially this mode over here. In the geometric mixture path, this mode shows up rather late. And by the time it shows up, you have no particles there. And you essentially have no hope of getting it. Even though this last mode has more weight than the first mode. So you could ask, is this a problem of the algorithm, or is this a problem fundamentally of the path? And I claim it's a problem of the path, because even if you could construct an algorithm that realized you needed to get over here, the velocity field to take you from here, where the probability is, to over here, would be very, very large all of a sudden. It would sort of, at a certain time, transition to becoming a very, very strong velocity field that pushes you over here. And that's a very difficult thing to capture. So the final vignette that I want to kind of close on is, well, what is the relation? What can we say more quantitatively about the relationship between the path that we pick and the velocity field that is necessary to realize the path? And could we actually pick the path in a way that guarantees better velocity fields? So this is, I think, a rather broad question for dynamic transport, and I could just phrase it in general, like, what is a good sequence of distributions, pi t, between any reference and any target? Good in what sense? I mean, so what have we seen? Okay, neural ODEs, you make no specification of the path. Regularized neural ODEs, well, maybe you can say, well, don't let the path get too crazy, control it in some way, or you can prescribe the path by being very, very specific. But in all of these, you need to somehow grapple with this underlying question, especially in the last one. You need to explicitly prescribe the path. But even here, you need to regularize the neural ODE in a way that you think is going to give you velocity fields that are learnable, that are nice to learn. So the kind of final vignette is kind of saying, well, a widespread folklore has been, and you should read a lot of papers about this, that say, well, straight line paths are good. Optimal transport, the dynamic formulation of optimal transport gives me kind of straight line paths through the displacement interpolation. Maybe that's a good thing to do. My claim is that it's actually not a good thing to do. In sort of tautologically, if you're trying to take a straight line path, as I showed you when we were kind of constructing the velocity field for straight line path, it begs the question of why you should be dynamic in the first place. Because if you're following a straight line, you say, well, I converge with one, say, explicit Euler step from time 0 to time 1. But all I've done then really is just parameterize the displacement. So I've really given up the potential benefits of being dynamic in time. So here is the claim that I want to kind of illustrate in the last point. We should balance time integration error with things like a velocity field approximation error. And we can do that by actually picking very specific curved lines. So how to find what is best? So I want to give you kind of a very, very simple example. I have a Gaussian, mean 0, with some variance at time 0 and a different variance at time 1. The optimal transport in 1D, you can write it down, it's this sort of linear interpolation. And this is the velocity field that realizes that straight line path. And if you look at the Lipschitz constant, the spatial Lipschitz constant of this thing, as a function of t, so essentially look at the gradient of this thing with respect to x, you find that as you get to t equals 1, this could blow up if the target is very concentrated with respect to the reference. So this thing could become arbitrarily bad if sigma 1 is small relative to sigma naught. If instead I decided to take this straight line thing and just reparameterize time, so I haven't even changed the path too much. I'm visiting the same sequence of distributions as I go from time 0 to time 1. I'm just doing it more slowly in some times and more quickly in some other times. So I've not made a radical change. All I've done is basically pick a clock that maps the unit interval to the unit interval that's always positive, but that could do some other thing. So here's what I get with a clock, an arbitrary clock tau. I could pick this clock in a way systematically that makes this velocity field much, much more regular. Now, how to do this systematically? So in some sense, like, how do I claim this? Let me chase the spatial Lipschitz constant enough. Let me say that's the thing I want to make small. I'm kind of low on time, so I'll just say, but here's the problem that we want to solve. I want to search over all possible clocks something that makes this thing small. I want to control this uniformly in time. I can actually solve this problem using calculus of variations. And the cool thing is actually you can explicitly solve this. And the result is an ODE that depends on kind of concentration properties of the reference to the target. And it gives you optimal schedules that slow down either at the beginning or at the end or something like this. And if I take the optimal schedule and I look at this Gaussian problem, actually this optimal schedule gives me something like this. The spatial gradient of the velocity is actually exponentially smaller than what I had in the straight line case. Originally, it was like sigma 1 over sigma naught, but now it's log of that. And it's constant over time. And it turns out this exponential improvement actually holds for rather general classes of source target distribution and transport. So here's kind of the picture. If I'm doing straight line paths from a fat Gaussian to a thin Gaussian, here I really suffer in terms of spatial regularity. Like if I look at this, the derivative of the velocity field here with respect to x, I'm going very strongly to the right over here, and I'm pointing very strongly to the left over here, very sharp. The optimal schedule does something like this. It tapers and it slows down. If I do something like map a unimodal distribution to a Gaussian mixture, I need to split a lot of mass over here, and I need to concentrate a lot over here. So I suffer the poor regularity here and poor regularity here. The optimal schedule slows down at the beginning and slows down at the end, and does something like this. So the point is things like this can give you exponential improvement. So maybe here is kind of the last slide. You know, this was a vignette, describes, I think, some work in progress, but I'd say overall, we're scratching the surface of how to design optimal schedules and optimal paths, which I think really is a question of how do you exploit dynamics. I think there's a lot of potential because you can get a lot of improvements, but we have to navigate this massive sort of design space where you could pick any transport to couple two distributions and any velocity field to realize a transport. You need to navigate this in a principled way. So there's a lot of things left to be done, and you can then exploit this in algorithms that are suited for generative modeling, algorithms that are suited for sampling, algorithms that are suited for sampling even when you can't calculate gradients. But the core question is, how do you design these kinds of paths? So yeah, well, thank you for your attention. Take some questions, and here's some papers that describe, you know, maybe some of what I've talked about today. Thanks a lot.
So thank you for such an excellent talk. So it's time for questions, and in the interest of time, please have your questions ready quickly, or you can unmute and ask the questions or raise your hand. If there are multiple questions, I will go over one after another. Yes, so I have a question from Heidi. Please go ahead.
Yeah. Thank you, Youssef. It's good to see you here. I really enjoyed listening to your talk. So my question is, I'm thinking how we can extend this idea of dynamics into neural networks. In particular, if you have, for instance, two inputs and one output, and it's going to be two input distribution and one output distribution. So my question is whether this can be extended to a transport from two distribution to one, as opposed to 1 to 1, or I mean.
And so when you say two distributions, meaning like sort of like, I don't know, a distribution that lives in RD and another distribution that lives on like RM, and somehow
Right. Yeah, that could be also one way to look at it. Yeah. What I was thinking was that maybe two distribution in R1 mapped one distribution in R, or you could play with the.
So okay, if I interpret your question, you're kind of saying like, you know, right now we're looking for like essentially like invertible maps from RD to RD. But would you do a better job of representing some desired distribution by mapping from some higher dimensional space, lower dimensional space, or vice versa, from some lower dimensional to some higher dimensional? I think, okay, it's an interesting question. So certainly if you believe your target distribution like lives on some low dimensional manifold, then these transports, you know, these are going to give you like non-degenerate distributions in the ambient space. So really, you should be thinking more about some sort of encoding and something that maps from a low dimensional distribution, something of the dimension of the manifold to the target, okay? Which you could do, but you would sort of have to put things around these sorts of tools. And this is, this then points to things like autoencoders and things like that, which, which you could relate to these things. People even do like diffusion models, but like in latent space or things like that. But the other question you asked, I think, is in my mind relatively open, is saying I want to represent a distribution RD, but should my source distribution be of dimension greater than D?
Mm-hmm. So
you're sort of giving up invertibility, right? Because now you're going to take, in principle, 2 points and map them to 1. But could that be an easier thing to learn? I'm not sure. I think it's a great question. The one bit of evidence I've seen is not in the setting of distribution learning, but just function learning. So there's some work in neural ODEs where you're saying, okay, the neural ODE cannot represent arbitrary functions from R to R, cannot represent arbitrary invariant functions. But you could represent arbitrary functions from R to R by making the input distribution actually higher dimensional and kind of introducing some extra degree of freedom, so points can sort of go around each other in the high dimensional space and show up where they need to be in the low dimensional space. So I've seen this done for essentially learning functions, which is a broader problem in learning distributions, because distributions are special. But it is interesting to consider, would this actually be advantageous for learning distributions? I don't know, but I think it's intriguing.
Thank you.
Is there any other questions? If not, we would like to thank the speaker now.